Hello, Chem 201 Organickers. Today we are going to talk a little bit about VSEPR molecular geometry theory. We're going to look at how you can actually look at a Lewis structure and then determine what three-dimensional shape that molecule is going to obtain using VSEPR theory. If you've had Chem 1 as a prerequisite, you're probably well familiar with this technique. If you had the other prerequisites, Chem 101 or Chem 110, hopefully you got to this. If not, I just want to make sure that you have a couple of key points in order to get everyone on the same page as we begin this course. The nice thing about this class in terms of organic chemistry is we only have to know the VSEPR theory and the molecular geometry for compounds that have 4 electron groups, up to 4 electron groups. This is different than a Chem 1 class where you go and you look at 5 and 6 electron groups, which are much more complicated. We basically just need to look at the geometry of carbon, since organic chemistry is based on carbon molecules. So let's go ahead and start talking about the valence shell electron pair repulsion theory, which allows us to determine the molecular geometry of carbon type compounds. So I'm going to share my screen, and we are going to start looking at a couple of slides. All right. So here we want to look at valence shell electron pair repulsion theory, which is considered another bonding theory. What we want to look at is the fact that a lot of properties of molecular substances actually depends on the structure of the molecule. So there's a technique, there's a model, it's called valence shell electron pair repulsion, or VSEPR or VSEPR theory, which is a simple model that allows us to account for molecular shape. We're going to use the Lewis structures that we learned how to generate previously. We're going to take that Lewis structure and define various electron groups that are attached to the central atom. And then based on the number of electron groups around the central atom, we are going to be able to assess and describe the three-dimensional structure for that particular atom. Electron groups are defined as lone pairs and any kind of bond. So single bonds are 1 electron group, double bonds are 1 electron group, and triple bonds are 1 electron group. The way that we can designate shape is we base the idea of geometry on the idea that electron groups repel one another through Coulombic forces. So what happens is I have negative areas of electron density which are negatively charged. Those negatively charged areas of electron density are going to repel each other because like charges repel. Based on this theory, depending on the number of electron groups that are around a particular atom, I can figure out the actual geometry around that atom and try to assess what its three-dimensional structure would be. So we're going to use electron groups around the central atom as a defining point as we begin VSEPR theory. We know that the electron groups around each central atom is going to will be most stable when they are as far apart as possible. This is called valence shell because those are the groups that actually engage in bonding. Electron pair, we're looking at bonds, or lone pair, repulsion theory. Those negatively charged groups are going to strongly repel each other. The idea is because electrons are negatively charged, they should be most stable when they are separated as much as possible. The resulting geometric arrangement will then allow us to predict the shape and the bond angles in the molecule. So here's an idea. Let's say I have my central atom, which is right there in the beginning. And let's say I have 3 electron groups around that central atom. Well, they're going to naturally orient themselves in this sort of equilateral triangle because this is going to minimize the repulsions. These atoms, 1, 2, and 3, are as far away from each other as possible. That is going to be the most stable arrangement of these atoms, which will minimize these electron pair repulsions. And because I have 3 electron groups, I know that when I look at this central atom and I consider the bonds to these 3 electron groups, that these 3 groups are going to orient themselves in this triangular geometry, and they're all these atoms are going to be in the same plane. So this geometry is going to be called trigonal planar. The Lewis structure predicts the number of valence electron pairs around the central atoms. So before I can do this, I have to draw the Lewis structure. Each lone pair of electrons constitutes 1 electron group on any central atom, and each bond constitutes 1 electron group. It doesn't matter whether it's a single, double, or a triple bond, it's still each one of those types of bonds constitutes 1 electron group. So for example, if I draw this molecule for NO2, this is my central atom. I have a lone pair, which is 1 electron group. I have a bond, which is the 2nd electron group, and I have a double bond, which is the 3rd electron group. So I have 3 electron groups around that central atom nitrogen. Those 3 groups are going to determine the geometry around that nitrogen. It is not going to matter these other lone pairs that are on these other atoms. These do not matter because they are not on the central atom. So any lone pair that are not on the central atom are not going to make any difference. What I'm going to look at is when I identify the central atom, I'm going to look at what's directly attached to that particular atom. There are 5 basic arrangements of electron groups around a central atom, and this is based on a maximum of 6 bonding electron groups. Each 5 of these basic arrangements result in 5 different basic geometries. If you took Chem 1, you're going to study you will have studied all 6 of these bonding arrays. But for organic, this is really nice because we only have to go up to 4 groups around a particular atom because that is what carbon does. Remember, carbon actually is going to be tetravalent. It has 4 valence electrons and it wants to make 4 bonds. We also know that carbon can have single, double, or triple bonds. So we have to be able to go up to 4 groups in order to be able to characterize various geometries around carbon. Now, if your molecule can exhibit resonance, it doesn't matter which resonance form I use, the electron geometry is always going to be the same. We're going to highlight resonance a little bit more later, but just to know what we're doing, we are going to study the molecular geometry that happens for carbon. So we're going to have 2, 3, and 4 groups around a central carbon atom. And using those electron groups, we're going to determine the basic geometry around various carbons. In order to do this, I need to first write the electron dot structure. So I have to have a valid Lewis structure for the molecules. And then I want to assess the number of electron charge clouds that surround the atom of interest. So this is typically the central atom. And in organic, it's usually carbon, nitrogen, or oxygen, or some halogen. So we're going to focus on those particular geometries. Then, once I have the Lewis structure, I'm going to predict the geometric arrangement of those charge clouds by assuming that I have this valence shell electron pair repulsion, and that assumes that the charge clouds are going to be oriented in space as far away from one another as possible. So let's look at when there are two electron groups. If I have two electron groups, they're going to naturally try to be as far away from each other, which gives me a linear geometry. So two electron groups about a central atom, I have a linear electron geometry. This bond angle, which is the bond angle between the atoms that are attached to the central atom, is 180 degrees. This is something you should know. Linear bonds are 180 degrees because those charge clouds want to get as far away from each other as possible. Again, you will see this carbon with two bonds, or you could see a carbon that has a triple bond and a single bond, and these are going to give you this linear geometry when we start looking at carbon compounds in particular. If you ever want to do this at home and sort of look in a three-dimensional model, all you have to do is blow up two balloons and hold them at the tie. You'll notice that they naturally orient themselves in this straight line. So if you have any balloons and you feel like playing with them, this is a good activity that you can do, and you can actually look at these geometries without making a molecular model. But again, in linear geometry, I have bond angles of 180 degrees. If I have three electron groups, what I'm going to see is I'm going to have the shape of a triangle around the central atom, and this is going to be the trigonal planar geometry. All of the atoms are in the same plane. So this is a flat situation, and here's where I get that trigonal geometry. The planar is because they're all in the same plane, and it's a flat molecule basically. These bond angles are 120 degrees. So this BF3 boron trifluoride is actually an example of this. Carbon will undergo this when I have a double bond and I have two triple bonds. This is going to be my trigonal planar geometry when I look at various carbon compounds, so keep that in mind. Again, if you wanted to look at a balloon, you could put three balloons about the same size together, and they're going to naturally orient themselves in this trigonal planar type of geometry. Next, I have 4 electron groups, which is tetrahedral. So when I have 4 electron groups around a central atom, I'm going to form the shape of a tetrahedron. So this is going to be my tetrahedral geometry. My bond angle is 109.5. So this is CH4, oops, CH4. CF4 will do the same thing, but this one is CH4. And what you'll notice is that I have carbon with 4 bonds, 4 single bonds around it, and this is the situation that carbon forms when I have 4 single bonds around a central carbon atom. This will take the shape of a tetrahedral geometry. And again, if I look at 4 balloons held together, I can clearly see that it forms this type of a shape, this tetrahedral shape, and if I connected all of the outside atoms, I would be able to draw the shape of a tetrahedron, which is where I get the tetrahedral electron geometry. So let's look at this. If I want to determine the molecular geometry of these different molecules, right? This one is actually from another slide. When we drew the Lewis structure of this, I ended up with this geometry. So if carbon is my central atom, I have 3 bonded atoms to carbon. I have 2 single bonds, and I have 1 double bond. I have 0 lone pair. So this is going to be 3 electron groups. When I look at 3 electron groups, I'm going to notice that I have about 120-degree bond angles, and this is going to be trigonal planar. My CH4 we just looked at. Basically, I have a carbon with 4 single bonds. So I have 4 electron groups because I have 4 single bonds. So this geometry is going to be tetrahedral. Now, lone pairs can actually affect what's called the molecular geometry. When I consider electron geometry, I'm looking at every electron that is around the central atom, which includes lone pair. The lone pair sort of dictate what geometry is going to form around that central atom. But if I actually want to look at the geometry of the molecule, I'm just going to look at the shape of the atoms as they exist in 3-dimensional space. So I count the electron pairs in order to get the electron geometry, but the geometry of the molecule is going to be the shape of the atoms, not including the lone pair. Now, lone pairs typically exert a slightly greater repulsion than bonding electrons, which affects the bond angles. This is because the lone pair is actually more spread out in space. It's really localized on one particular nucleus, so it is not attracted and spread out between 2 nuclei as you would have in a bonding pair. You have this lone pair that's localized on 1 nucleus, and therefore it sort of crowds around. So in order of electron group repulsions, a lone pair interaction is the most repulsive. Those electron lone pairs will want to get as far away from each other, which is usually a little bit more than the ideal bond angles. A lone pair bonding pair is also the next strongest electron group repulsion, and then the bonding pair is the weakest electron group repulsion. So if I have a lone pair, I have to consider 2 different things. All of these atoms here, this guy has got 3 electron groups, right? It has 2 single bonds, and it has 1 double bond, and it has 0 lone pair. So the electron geometry is equal to tetrahedral. The molecular geometry, actually that electron geometry, is equal to trigonal planar. Sorry about that. Is equal to trigonal planar. The molecular geometry is also equal to trigonal planar because there are no lone pair. If I have no lone pair, the electron geometry is the same as the molecular geometry. The lone pair actually comes into effect shaping molecular geometry because it's not counted in the actual shape of the molecule. So for example, this guy down here, let me use a different color to be clear, right? This has got electron group is 3, I have one double bond, I have one single bond, and I have one lone pair. So my electron geometry is going to be trigonal planar. But now here's the thing, if I just look at the shape of this molecule, the shape of the molecule is actually the shape that these atoms make, which is not trigonal planar. This makes the electron geometry trigonal planar. This makes these bond angles 120 degrees, right? Roughly, maybe a little bit larger here because this is going to take up so much space. But the actual geometry is just if I draw lines connecting the atoms that are there minus the lone pair, and that molecular geometry that I'm describing now is going to be bent. So hopefully this brings back memories from when you did this in your prerequisite class. The other shapes that we're going to talk about when there are 4 electron groups and one or more is a lone pair. I have a trigonal, or I have a pyramidal shape or a trigonal pyramidal shape because this type of situation forms a triangular base pyramid. And then when I have 4 electron groups and 2 are lone pair, so this is 1 is a lone pair, I get that trigonal pyramidal shape. Here I get this bent shape. So if I look at that, I can see this slide. Here I have 4 electron groups, 0 lone pair. So my electron geometry is equal to my molecular geometry, which is equal to tetrahedral. Here, right, this bond angle is a little bit less than 109.5 because this lone pair takes up more space and is a more repulsion with these other bonds. So that bond angle collapses a little bit in this particular geometry. So this is still going to have an electron geometry of 4 electron groups, which is tetrahedral. But now I'm going to look at the fact that I make this 3-sided pyramid. If I take away this lone pair, so my molecular geometry here is going to be trigonal pyramidal. Here, again, this is going to be extra repulsive, right? But my, so this is going to be greater than 109.5. And then this is going to be less than 109.5 because those lone pair are have extra repulsion with one another, again collapsing that tetrahedral bond angle from 109.5 to more like 104.5. You don't really have to know these numbers. What you have to know is the lone pair will collapse those bond angles. So when I look at the electron geometry, I still have 4 electron groups, so I'm still tetrahedral. But because of those 2 lone pair, I have a molecular geometry which is bent. And again, I'm just looking at the shape that the atoms make without the lone pair. I'm looking at the shape, if I just connect the dots with the atoms, I get this bent molecular geometry. And these are the ones that I really have to focus on. In particular, I have to look at the ones that we talked about on this slide, where I can get this trigonal planar and also this bent shape with 3 electron groups. And then I also want to make sure that I know the tetrahedral geometry for electrons, as well as these other molecular geometries when I do have the inclusion of lone pair. So this is a chart. This is the kind of chart that you want to look at. These are the electron and molecular geometries that are particularly important for carbon. So these electron geometries and these molecular geometries are things that you're going to have to know. Remember, when my lone pair is 0, my electron geometry is equal to my molecular geometry. It's only when I have these other lone pairs, when I have 1, or in case 1 and 2, when I have those geometries, that all of a sudden they're going to be different. So these are the things that I have to consider. The presence of lone pair also collapses those bond angles so that I have less than the ideal bond angle that I'm expecting, because those lone pairs are localized and take up, or actually end up being more, having more of a repulsive effect with the other electron clouds. So just one more thing. A lot of times when we're looking in organic chemistry, we're going to try to show three-dimensionality in a plane of paper. So we're going to be looking at a lot of drawings where I'm looking at straight lines, I'm looking at solid wedges, and I'm looking at hashed wedges. So a straight line is just a line. A solid wedge is actually sort of filled in like that. And a hashed wedge is something like this. This is in the plane of the paper. This is behind, or actually coming out of the plane. And this is behind the plane of the paper. So a lot of times I'm going to be putting these bolded and hashed wedges in my structures in order to look at trying to impart a three-dimensional structure to a two-dimensional drawing. So again, I want to look at the straight line, the hashed wedge, which indicates it's going into the paper, behind the paper, and this bolded wedge, which means it's coming out of the page. So this can be applied from each atom to that is a central atom. And when we're going to see, what we're going to see in organic chemistry is that many of our molecules have multiple central atoms. So I have a structure that has 4 or 5 carbons. I have a structure that has carbon, oxygen, and nitrogens. A lot of times I want to try to get an overall three-dimensional shape for those as well. And when I do this, basically, I use the VSEPR theory to assign geometry, both electron geometry and molecular geometry, around every atom in the sequence. So here I have 1 central atom, 2 central atoms, 3 central atoms, 4 central atoms. I have the nitrogen, the carbon, the other carbon, and then this last oxygen on the right. If I look at this, right, this is going to be electron geometry is tetrahedral, but I have 1 lone pair. So this is going to be my molecular geometry. This leftmost carbon, I have 4 electron groups. I have 0 lone pair. So my tetrahedral is going to be my electron geometry and my molecular geometry because I have 0 lone pairs. This guy here, I have 3 electron groups, 0 lone pair. So this trigonal planar is going to be my molecular geometry as well as my electron geometry. And then this last guy here, I actually have 2 lone pairs, right? This oxygen has 4 electron groups. So the electron geometry is tetrahedral, but I have 2 lone pair. So this bent is going to be the molecular geometry. And those, I can also characterize bond angles, right? If I have a lone pair, the bond angles for this trigonal pyramidal is going to be less than my tetrahedral 109.5. Same thing with this oxygen. Those bond angles are going to be less than 109.5. This is going to be very close to 109.5 all the way across because it's tetrahedral. And then these bond angles are going to be roughly 120 degrees because that is going to be trigonal planar. So if you see a structure that has multiple central atoms, what you're going to have to do is draw the Lewis structure first, and then use the VSEPR geometry charts to figure out both the electronic and the molecular geometry around every one of the central atoms in the molecule. This is glycine. This is an amino acid that is prevalent in proteins and biochemistry. And it has, again, as we mentioned, those 4 different central atoms. Each one of those atoms has its own particular geometry. And then when I look at it all together, this would be a diagram of a molecular model. If you actually have a molecular modeling set at home, which is extremely useful for introductory organic as well as regular organic chemistry, and you build this guy, you're going to be able to see the trigonal pyramidal, the tetrahedral. You're going to be able to see how all these geometries look together and they correlate well with what you would predict with the VSEPR geometry when you actually look at it in a molecular model. And that is all for VSEPR geometry. Again, it's a little bit easier than maybe what you were used to if you took Chem 1, because I only have to go for 2, 3, and 4 electron groups. I have to basically look at the type of VSEPR geometry that carbon makes, that linear, that trigonal planar, and that tetrahedral geometry. And then I have to also assess these heteroatoms, these atoms that are not carbon, nitrogen, oxygen, that kind of thing, in order to get my overall 3-dimensional structure of molecules. So if you weren't an expert before, hopefully you are now, and this helps as we move through this course. All right, that's all for VSEPR theory.